This is Preeti Choudhary. I am presenting on the behalf of Professor Subhash Thota. My topic is low field magnetization switching and exchange bias in SmMnO3 based perovskite. Outline of the presentations are introduction, literature review, experimental methodology, applications, result and discussion, and conclusion. So introduction, perovskite material which have a journal formula which is ABX3, where A and B both are cation and X which is anion, which have certain O negative kind of charge, and both A and B, where we have chosen samarium as a rare earth material, and B, which is manganese as a magnetic material, which have a orthorhombic crystal symmetry with space group PB and B, where a cation have a 12 number of coordination and B cation have 6 number of coordination. We are talking about SmMnO3, rare earth perovskite, which is doped with Fe element. It having a uh, two coordination, where poses SM SM3 positive cations, and B have Mn3 positive as well as Fe3 positive cations, which poses certain unique properties like tunable magnetization and spin switching. So there are certain literature review why we are choosing Fe-doped SmMnO3 material. When we are talking about the single crystal SmFeO3, which have a good spin switching application, as reported in a literature review. We are again, there is another paper which have reported when we have doped Mn25%, when we have doped Mn 25%, which have again it shows spin reorientation property. Then there is another paper which is basically comparison between single crystal and we are looking for comparison between single crystal and polycrystalline material. uh, Polycrystalline material. So our motivation is, when we are looking for Fe doped SmMnO3 polycrystalline perovskite, exhibit certain tunable magnetization property which enhance exchange interaction and improve electron spin coupling, and it's enabling low energy magnetization control, and it's also have certain exchange interaction and stability of material, which is useful for device application and more other application like non-volatile memory, magnetic sensor, and spintronic logic. So our aim is, first of all, our aim is to do comprehensive study of polycrystalline material of Fe-doped SmMnO3 material with single crystal. So there is a literature review where we have seen field dependent magnetization study, where spin orientation due to canted spin. So we synthesize a polycrystalline material SmMnO3 with Fe doped by Solgen method, where our precursors are our starting material, which is nitrate based precursors, samarium nitrate, Mn nitrate, and Fe nitrate, and we dissolve those nitrates in ethanol solvent and use oxalic acid as a chelating agent. Then we do we after mixing all the starting material, we do for certain hours of stirring, then drying those samples and for overnight, then calcine at 800 degrees and 800 degrees Celsius for 6 hours, then centered at 1150 degree for 12 hours to convert in a powdered form. Make a bulk sample by pressed into padlet by hydraulic press, which are shown as a uh, evidence of experiments. Application of Okay. Applications of SmMnFe MnO3 doped material are magnetic sensors, non-volatile memory, high-speed data processing, and spintronic logics. These are certain applications which are can be used by FEDOPed SmMnO3 SmMnO3 sample or polycrystalline material. So our preliminary results, when we go for the XRD, then we have confirmed that SmMnO3 polycrystalline material have a orthorhombic crystal structure which have a space group PbNm62, and after that we do some magnetic characterization and compare with the single crystal. When we compare with the single crystal material, then we look into that single crystal material compensation is about 9 Kelvin, while for polycrystalline SmMnO3 compensation temperature was very 9 Kelvin to 4 Kelvin. And on the other hand, when we vary the magnetization, DC magnetic field, then we see at 500 Oersted there is no compensation. But when we go to the low magnetic field, then there is a compensation which is around 4 Kelvin in SmMnO3 polycrystalline sample. So after that, we doped 2% of SmFeMnO3 perovskite, where we see after after magnetization we go for certain another parameters to calculate. First we do first we plot the chi first we plot chi versus one inverse temperature, where we evaluate temperature independent susceptibility, which is around minus 89 into 10 to the power minus 4 EMU per mole per Oersted. And then there is a theoretical calculation, which is Kai Harty-Fogg, which is reported on a certain literature, where we from there we evaluate. This is theoretical one is minus 1.37 into 10 to the power minus 4 EMU per mole per Oersted. After getting temperature independent susceptibility, we go for modified Curie-Weiss law, where we calculate all the parameters like constant Curie constant and Weiss temperature and effective magnetic movement and effective exchange constant. So by interpolating the data, we get C, which is 1.96 EMU per mole per Kelvin, and Weiss temperature, which is minus negative, which represent the antiferromagnetic property of SmMnO3, which is around minus 185 Kelvin, and effective magnetization moment for polycrystalline SmMnO3, which is 4 newbie, and exchange constant, which is effective exchange constant is around 0.66 milli electron volt, which is calculated by mean field theory. Which is shown, where formula is shown below, with effective is equal to 3 kb into Weiss temperature divided by 2Z, which is Z is equal to 2E, where charge is plus 3, and S into SS plus 1. Then we go for another doped sample, where X is equal to 2%. We do Fe 2% to see the what are the changes we have seen different from single crystal. So our when we doped 2%, then compensation temperature, which is tuned by 2.4 Kelvin. As we see our previous sample, which is pristine SmMnO3, which have a compensation temperature 4 Kelvin. After doping of Fe 2%, we get 2.4 Kelvin compensation temperature. So we can say we can tune the compensation temperature by doping Fe material. So after evaluating compensation temperature, we go for further analysis, which is which is interpolating chi versus T inverse interpolating high temperature susceptibility, interpolating high temperature susceptibility, we get temperature independent susceptibility, which is around minus 40 into 10 to the power minus 4 EMU per mole per oerstate. And the theoretical value is around minus 1.37 into 10 to the power minus 4 EMU per mole per oerstate. Then there is where we can clearly see our effective magnetic movement and exchange constant is also tuned when we dope the Fe, which is clearly change our vice temperature from minus 187 to minus 227 Kelvin, and effective momentum, which is which is around 0.6, there is a 2.2 newbie, and exchange constant which is tuned by 2%, which is 0.82 milli electron volt. So our conclusion is, when we do the comparison of how magnetic temperature dependent property differ with the polycrystalline sorry comparison so we can say comparison of how magnetic temperature dependent property differ between a polycrystalline crystalline sample versus a single crystal sample. Polycrystalline SmMnO3 shows a field dependent comparison temperature, which is not shown by a single crystal. So Fe doped symmetrically lower peak compensation, and we can modify new magnetic movement and exchange constant by doping Fe, and we can see then there is a compensation temperature vary by Fe doping with the magnetic field, or we can see by changing magnetic field there is a change in compensation, or by temperature there is change in compensation temperature. So after that we can say that magnetic behavior is strongly influenced by microstate in polycrystalline sample, and these properties which are tunable, which helpful for further application like spintronic devices and memory devices. Thank you.